Hello guys, how are you? Everything is all right. Good. Okay, so last time we explore the coding of breadth first search in C++. Okay, and I published a homework based on that. It's depth first search in C++. So I just published there the code, the main structure we can say, and there are some parts that you should fill according to the description. Okay. So today's lecture, we're gonna finish all of that. Okay. I'm gonna show you the coding, C++ coding for Dijkstras. Then the assignment will be something similar to the previous assignment. The C++ main structure of A star, and we should complete it based on the instructions inside the file. Okay. It will be, pretty short lecture because we already know the basics of Dijkstras and also how we code in C++, some similar stuff like breadth first search. So I'm sure it will be good. Okay. So we're gonna take small example, small map, just to refresh our information about Dijkstra. It's the same example that we took last time and solved it with breadth first search. But now we're gonna add the cost because we assumed before that every cell has a cost of 1. But now I will add some cost to see. Okay. So let's start first by numbering the cells or giving them ID 0, 1, 2, 3, and this is the goal. 4, 5, 6, 7, 8, 9, 10, 11, 12. This is the start. 12, what else? Yeah, 13, 14, 15. Okay. So for the cost now, we're gonna assign 1000. So the cost of that cell, let's highlight it with yellow. So the yellow cell cost is 100. So if I move from any cell, for example 13 or 10, to that cell, the cost that I will consume is 100. Any other cell cost is 1, just 1. And to avoid any confusion, I just put the cost of the start node with 0 and the cost of the goal node with 0 also. So to avoid any confusion, because the start node is our start, we have no choice for that. We must start from the start point. And for the goal cell, we also have no choice. We must reach the goal. So I just put a 0 for it. It doesn't matter. You can put any number. Okay. So let's see how we're gonna do that using Dijkstra. algorithm. Okay. Okay, good. So let's see. I will start from here. So our first frontier, we're gonna have a FIFO. So Dijkstra's use FIFO just like, I'm sorry. We need also a data structure, something similar to the FIFO, but with different properties, different characteristics, to reflect what Dijkstra's need. So what Dijkstra's need is to choose the frontier with the minimum cost from the start. Okay? So for each step, when we explore, we will update this cost from the start. Then when we finish exploring a frontier and choose a new one, we're gonna choose the one with the minimum cost to the start node. Okay, so let's do that. So, yes, and the data structures that we're gonna use that reflect that characteristic is called priority queue. So Dijkstra's need something called priority queue. It's a FIFO, but it has a very good characteristic. So behind the scene, when you create a priority queue, it automatically sort the content inside this queue. For example, a very, let's add a page here. So priority queue. In C++, there is something called priority queue. So let's define one. So this is just a pseudo code. Priority queue of queue, for example. So we have now a priority queue called queue. Queue.push 50. Queue.push 10. Queue.push 25. Whatever. Okay. If this is a FIFO, if we check here, if this is a FIFO, the content after step 3 will be in that way: 50, 10, 25. And that's the head of the queue, and that's the tail of the queue. But priority queue, if we check after step 3, it will not be that of FIFO. It will have a different content. This is actually the order by which they were stored in the FIFO. But the priority queue will sort automatically the content of this queue. So you will find if the sorting is from minimum to maximum, you can control that. It will be 10, 25, 50. If you choose in the definition of the priority queue to sort the elements in ascending way from the minimum to maximum. So although we stored 50 first, it was the tail of the priority queue. And although we store 10, not the first element, but now it's the minimum one. So the sorting of that queue will make 10 at the head of the queue. So that if we make, for example, C out here, queue dot top, the top element, we will print 10. If it's just a queue, not priority queue, it will print 50. Okay, that's very nice because that's exactly what we need. So we're gonna create a priority queue in that way. such that this queue, each element is a pair. What is this pair is? It is the ID of the node and the cost from the start. So for example, if we store it in that way, node 1, for example, the cost was 5. Node 13, the cost is 2. Node 40, the cost is 3. If we define a priority queue like this, at some point in the future, when we try to read the content of this queue, it will be ordered in that or sorted in that way after sorting. This sorting happens behind the scene. You will not see it. But once you try to read something, it will be ordered, don't worry. So it will be something like this. If they are stored about, of course, we're gonna sort them based on the cost. So this one has the minimum cost, so it will be 13 and 2. This is the second one, 40 and 3. Then 1 and 5. So you can store, push whatever's there. And behind the scenes, something will sort them out for you. So when you finish exploring some frontier and try to read the next frontier, for example, in that example here, you will read this one. So you will explore node 13, this cell, which has a cost equal to 2 from the start node. And that's exactly what we're gonna do for, for Dijkstras here. Okay? So we're gonna store any cell we explore in a priority queue. This priority queue will each element, or each entry in that queue is actually pair of numbers. The ID and the cost. And behind the scene, these elements will be sorted based on the cost. Okay? So in the beginning, we have, so this is the priority queue. In the beginning, we will have the node 12 with cost 0. And of course, when we read it, we will read this is just one element there, so we read it. Then we explore around. This is out of the map, an obstacle. We have only 13 to explore. So we're gonna add to the queue $13. And how about the cost? The cost to go to that node is 1. And the current node, the current frontier has a cost of 0, distance 0 from the start. So the total distance from the start is 1. 0 plus 1 is 1. Since we finish exploring this, we remove it from the queue, not to choose it in the future. Because if we leave it there, it has the minimum cost. So we're gonna remove it from the queue. So, okay, so we add this, then we remove it by pop. So we'll end up with that one only. That's completed. Now we're gonna choose another frontier. Where we get our frontiers from the priority queue or the queue in general. We have again one node which is 13, but 13 now has 2 neighbors. This one is already explored, visited, so we will not visit it again. And this is out of the map. So we're gonna push 2 new elements in the node, in the queue, in the priority queue. 14. And again, the cost to go to 14 is 1, but the current cost, the current distance or cost from the start is 1. So 1 plus 1 is 2. To reach this node from the start, we need to make, you know, cross two cells like this. And we also explore 9, node 9. And what is the cost? The cost is 1,000 of that cell. And the current cost is 1, so 1,001. We finish exploring 13, so we remove it from the queue. So we will end up with only 2 like this. And they are already sorted for us. So this one in the beginning, you know, 14 and 2. So we'll start by 14. 14 again has 2 neighbors. This one and this one. So we're gonna push. $15. And what is the cost? The cost of that one is 1, but the cost of 14 is 2, so 3. Total is 3. And we're gonna push 10. The cost is again 1, but the cost of 14 is 2 from the start, so 3. We finished exploring 14, so we remove it. And now we need another frontier. Now, without making any concern about the priority queue, when you choose the priority queue will give us either this one or this one. So it will be sorted automatically behind the scene. So don't worry about that. When you read, you will find it like this: 15, 3, 10, 3, 9, 1001. So what is the head? The head is 15 and 3. And you may find the head is 10 and 3. I'm not sure what's behind the scene happens to choose between if the two, maybe first come, first serve, it's something like this. Maybe. But you will choose one with minimum cost. Don't worry. So we choose 15. 15 has only one neighbor to explore, which is this one, 11. So 15, 3, 10, 3, 9, 1001. And then 11, and the cost is 1, but the cost of 15 is 3, so 4. The distance from the start is 4. In that way, 4 cells, each one is 1. We finish 15, remove it. Choose another frontier. Again, if you try to read something, you will find it sorted. 10, 3, 11, 4, 9, 1001. So you will find that the head of the priority queue is 10 and 3. It is the minimum. This node has a cost of 4. This node has a cost of 1001. So we're going to explore 10. When we explore 10, we'll add 2 new nodes. Just one node, because this is visited already. This is also visited, okay, which is 11 here. Right? This is 11. So we only add 6. So we're going to add 6 now. 10 and 3, 11, 4, 9, 1001, and 6. And yeah, 6 has a cost of 1, and 10 has a cost of 3, so the total cost to reach 6 is 4. We finished 10, we remove it from the queue. We need another frontier behind the scene. This will be resorted: 11, 4, 6, 4, 9, 1001. Always this guy go to the back, the tail of the priority queue. If we choose 11, 11 will add another node which is 7, because this is explored before, this is explored before, this is out of the map, only 7 will be added. So we're gonna add 7, and the cost is 1, but the cost is 11 is 4, so 5. We finish the 10, we remove it from the queue. Now, this will be resorted. It will be something like this: 6 and 4, 7 and 5, 9, 1001. Again, this guy is a tail. And our newcomer becomes a second because it has a cost of 5, but 6 has a cost of 4. But 6 has nothing to explore because 7 is already explored. This is explored, wall and wall. So we just remove it without adding any other stuff. And now we choose another frontier, which is 7. 7 will add our goal now. 7 and 5, 9, 1001. And the goal, which is 3. And the cost is 5 plus 1, 6. Because the yeah, this guy has a 0 cost. So 5 plus 0 is actually 5. It doesn't matter, don't worry. If you put 1, it's okay. It's okay. We finish the 7, so we remove it. We need a new frontier. Behind the scene, you will find that this will be resorted. And the 3 and 5, which is the goal, now become the head of the queue. And when you take it as a frontier, you will find it's a goal, so we finished. We break the loop. And there are some steps that I didn't mention because it's default now, that in each iteration, or when we explore a new cell, we mark its parent at its current frontier. So based on that, we know the parent for each cell. So we can trace back until we reach the start point to know the shortest path. And you will find that the shortest path avoids this cell here with cost of 1000. Okay, that's Dijkstra, but with the concept of priority queue. Okay, now let's see that in our coding now. So we're gonna share the other screen right now. So I'm just, I build this is the same breadth first search coding. I just put another function because of course in the main function you can call whatever function you want. So I kept the breadth first search function there, but I added a new function which is Dijkstra. Okay. So let's see what we have here. Same examples again, but I added now a new array called cost. I assume, of course, that you have read and studied this code before, right? Because I asked you last Monday to do that. So I hope that you studied the code. Did you find anything, any problem with this code, any issue, something you can say you can't understand? Everything was clear? Okay.
I mean, it was clear with your video, but not by itself.
So when you studied it, it was not that it was not that responsive with you. I mean, you find many parts that you can't understand or can't digest.
Yeah, there was a lot of functions that I didn't really understand, like a lot of lines of code, and I was wondering if we could talk about that, but I would like to see how the Dijkstra's code looks like.
Okay, so I will go back, because again, the same structure, so mainly the same code, most of it is there. Of course, there are other changes to reflect Dijkstras, but mainly it is the same. So okay, we're gonna go line by line and see. Okay, but when I catch a line that you say that you saw before when you studied and you can digest it, let me know. Okay.
Okay.
You guys are using Visual Studio or something else? That's very important.
Visual
Basic,
Studio.
good, because if you are using something else, I'm not sure about its capabilities, but with Visual Studio, everything is easy because you can debug very easy in Visual Studio, okay? Especially the newer versions, like 2.15 and forward. It become very powerful. So let's see. Okay. So again, the first part of the code is just examples, it's hard-coded examples. Okay. So again, when you choose, if you want to choose any map or any example, just write its name here. So it will be the only one that is defined. So it will be the only one that will be chosen by the compiler. Okay. That's it. This shouldn't be hard. So let's continue with example one because it's easy and traceable. So it's 4x4 map. Okay. The ones are obstacles, 0 are free cells, is a start node, and G is the goal node. Okay. And I just created another map which is the same, exactly the same dimensions, but with the cost in it. So this means the cost of 0. This means the cost of 1,000. And this means the cost of 1. Okay.
Mr. Mustafa, for the int cost, why do you only include the column size? Why don't we have to take
Yeah, you can do
row?
both. Yeah,
the row?
yeah, that's right. You can do both. So it's a kind of cool stuff that you just try to. You only need one of them, and the compiler will figure out the other one. That's it.
Okay.
Because you initialize. Actually, it should be. The both should be, but for some reason the compiler needs at least one of them. But you can do both. That's fine. It's a feature in the compiler that can detect the other dimension.
Okay.
So let's keep it in that way. That's fine. Good. So good. So just examples. As I said, if you want one of these examples, just change this macro to the new name. So it will be the only one that is defined. So this will be only the one that will be compiled. The other will not. Okay. So basically, just to make you understand more this coding here. So what I'm saying is that if you have a defined macro called example1, do that. Okay. Okay. If you don't have a macro, which is not the case now, called example1, but you have another macro called example2 defined, then do that. Okay. So that's how to understand this part of the code. So for example, if we don't have a macro called example1, but now we have a macro called example2. So example1 macro, there is no macro defined called example. There is no macro here called example1. We have something similar, but it's called example2, not example1. So this is not defined. So this will not be translated, we can say. It will be ignored. But else, do you have a macro called example2? Yes. There is a macro called example2 defined. So do that. And of course, escape afterwards. Don't complete the check. Don't check this condition or this condition. Just like normal if else in C or MATLAB or whatever. Okay. So let's continue with example 1. what else we have? Yeah. Okay. This function is just showing the map. And that's used for debugging. If you want to trace what's really happened, okay, step by step, you wanna show the map, your map, okay? Okay. So to show the map, you send it to the function. And your map has look, it's a char type. So any element inside the map is of type char. Okay, character, basically. So here you are sending the map, then you loop over the map to show what's inside. I think this is clear.
Why do we
Yes.
use void here? And is show map just whatever you call the function? Or
Yeah, that's right. So basically we use void here because we are not returning anything. There is no return. If you notice, there is no return here.
I see.
Okay, it was not there. So it return is void. Okay, it only shows something on the screen, on the console window. This black screen that when I run, it appears. Okay, so that's why I use void. We don't need something because we want to just show something. We don't want to calculate something and return it. Okay.
And
Yes.
input map ij just returns whatever character is in
row I and column J.
Okay.
Yes.
And the /t is just to
Yeah, this guy here. Okay, you want to show the character, then space, the other character, and so on, right?
okay. So it spaces like the lettering.
/t. Oh my. /t means tab space, or a space with length equal to 1 tab. That's why it's called a T. So let me explain what is this tab stuff. Okay. So, okay, if you want one space, you just hit the space bar, okay, in the keyboard. And it's literally very short distance, right? If you want big distance, you hit the tab key. It's longer, right? Again, this is one space. Look. Now this is one tab. Okay. So tab is a space, but longer. Longer space. Okay. And after printing one row, I make end line. So I go to a new line. So it will print it in that way. Exactly that. So print line, row, I'm sorry. Then go to another line and print the other row. Go to another line, print the third row, and so on. Here is I'm just printing what's inside the map to understand the notations, the symbols. And if you want to break after each C out, you just hit break. If you want a slow output, then you can wait here for some time before showing the other C out. That's it. Okay. We need parent. Each cell, when we explore, we're gonna assign a parent for this cell, for the cell that we explore right now. Okay. So here in the main code, I define an array, or not array. I define a dictionary, and a dictionary is defined in C++ using the keyword map. Any entry in this dictionary is actually tuple, or any entry has two attributes, we can say, to to any element, any entry is two elements. One of them is the node, the other one is its parent. Okay, and the name of the map of this map or dictionary is parent. Okay, and how many entries in that dictionary is actually the size of the map, because each cell might have a parent. So if you have 4 by 4 map, 16 cells, then each one might have a parent. So you need a dictionary of length 16, which means it may have 16 entries. Okay. And here is how you insert each two elements in one entry. So each entry in the dictionary is actually pair of values. Yes, we can call it pair. That's very nice. So each entry is a pair, ID and the parent, the ID of the cell and the parent. And here is how you define a pair in C++ using this word, pair. Okay, so here you add the cell, okay, and it's there. In the beginning, of course, before exploration, we gonna initialize any parent with -1. That will mean for us that it's not explored, so it doesn't have a parent because it's not explored yet. Okay, you can choose any value rather than -1, but something meaningful. Okay. This part here, this Q item, is something similar to the pair, but it's not a pair. So the pair defines two values, okay? But this guy is defining many values in the same entry, not only two. Here we're defining 4 attributes for any entry. But we use this for Brits. We will not use it today, okay, in our Dijkstra. But basically, you are here defining a class called Q item, which means for Brits first search, any entry is in the queue, in the FIFO, is of type Q item. So it has 4 elements, or yeah, you know, it's not a pair right now because it has four stuff. Basically, each node is defined by its row, its column, its ID, and its distance from the start. How many hops from the start? Okay, that's why we need 4 here. So we are not gonna explore this again, but of course, if you have a question, just let me know. But we're gonna explore Dijkstra's algorithm. So this is a function that implements Dijkstra. Okay. Of course, it reads the grid, the dictionary that you store the parents in there, and the start node and the goal node. Any one of you guys don't know what is this exactly? What is this ampersand here is doing? Don't be shy.
By reference.
What? Yes, it's
And by
called,
reference.
yes, that's right. So this is called the call by reference. So actually, these 3 variables are initialized, are defined in the main function. So when I send them in that way or pass them in that way to this function called Dijkstra, I am passing them by reference. So any change in their values inside this function called the Dijkstra will affect their values in the main function as well. Okay. Okay. Inside this function now, again we have this visited array in which we remark any cells that we visit by 1, so we don't explore it again in the future. We define just 2 variables to hold the start row and the column node row column. Yeah, the start node column and the start node row. Okay. Then in the beginning, we mark. So in the code, you're gonna just get a frontier, pick a frontier, and explore the nodes around it. Okay. And like MATLAB, if there is a neighbor that is wall or obstacle, then you're gonna exclude it. Okay, you're gonna get another neighbor or whatever. And also if it's visited before, explored before, you're gonna also skip and get another neighbor. But we can combine these two separate checks in one check. So instead of making two checks, if it's barrier, then checking if it's visited before or not, we can mark all the barriers as visited. Just a model, okay? So we just make one check. If it's visited, whatever it's barrier or not, but visited, then we will escape it and get another neighbor. And that's what we are doing in here. And as a byproduct, when we find the start node, because we don't know the start node, by the way, we read the map like this, but you notice here there is no specific variable called variables that hold the column and the row of the start node or the goal node. So when we go in that loop, this first loop is the Dijkstra's function. When we find the start node, as a byproduct, okay, store the row and store the column. Okay, and also get its ID. And the ID of any node is equal to the row coordinate plus the row size, how many nodes in the array, plus j, the column coordinate. The same for G, but for the goal we don't need the row and the column. We only need the ID. And here is the Dijkstra's part now, because this is the first difference. So until this point, everything is similar to Brett's first search. Now here I am not defining a stack or a FIFO like Brett's first search or Depth's first search. No, I am defining priority queue. And this priority queue will take in each entry a pair. And this is how you define this pair. Just, don't worry about the details. Just take it like this, okay? And here is the option that you should vote in order to sort its element ascendingly from minimum to maximum. Okay, that's the part or the options that do that for you. And the name of the priority queue is BQ. Okay. So the bottom line of that line here, we are defining a priority queue. Each entry in that priority queue is actually a pair of values, the cost and the cost of the node, which is integer, and the ID of the node, which is also integer. So that's why I'm calling it a pair of integer and integer. And I will sort the entries in that queue ascendingly from minimum to maximum. And the name of this priority queue is PQ. As usual, what is the first element that we usually add in the queue in whatever algorithm we took so far? It is the start node. And here I am pushing the start node inside this priority queue. Since we need a pair of values, that's the function or the keyword that creates this pair for you. Okay. So our pair will be the cost of the node and the ID of the node. In that case, it's a starting node. So that's why we need the row coordinate and the column coordinate of the start node. Okay, and also we need its ID. And we need to get the cost, we read the corresponding value in the cost array, this array. that I created for you. So for example, the cost of 0 and 3, row 0 and column 3, which is this one, is 0 right now. And guys, the order here is matters. So which is before which is matters. I mean, you must put or store the cost before the ID. Because when the priority queue will start to sort its element, it will look at the first element in each entry, in each pair, which is the cost. So you must put that as a cost, because we wanna sort them based on their cost, not their IDs. Okay. Good. And we mark this cell as visited. So in the future, when we choose another frontier beside this node, we will not explore it again and put in the priority queue. Good. So while the priority queue is not empty, while still there is frontiers to explore. So read the top element or entry, top entry in the priority queue. And again, the first element in the pair is the cost. So this is the cost of the frontier to the start node. Now, since this is the start node, this is the first node, to be 0. And the ID is the second element in the first entry, or the top entry, or the head entry of that priority queue, which is ID. Then we pop this element. We can pop in the beginning or at the end. That's in the example that I just solved with you on the tablet. We were popping or removing the frontier from the queue at the end. You can remove it in the beginning because you already get its ID. That's what matters for you. We determine the row and the column, and here is how you will convert back from ID to row and column. This is actually the opposite of this. This is how to convert row and column into ID. This is the opposite. And again, if the current frontier is the goal, just break and return its cost from the start. This will give you the total cost to reach the goal node from the start node, which is pretty useful. We don't need to calculate it again. Once you pick a frontier, just mark it with F. That's what happened in that code. Except the start node, because we always need to mark it as a start to know where is the start and where is the goal. But you can do it as if. That's very fine as well. That's fine. That's my choice. Okay, now we're gonna explore around the frontier. So we move up, then right, then left, then down. So let's see what's happening in any one of those. To move up, that means the row that is above me, which is my, and that row is actually the current row of the frontier -1. So I am saying if row -1 is larger than 0, that means it's inside the map, okay? Larger than or equal to 0. And not visited before, that cell above me, which has the same column but row -1, not visited, then visited. Visited. So we're gonna read its ID. Then we're gonna push its cost and the ID into the priority queue. What its cost? It is the frontier cost, its parent right now, plus its cost itself. And this is its ID. And set its parent to the current frontier. and mark it as visited. Here we increment the step counter to track the something related to the time to explore. And we show this newly added node to the priority queue as asterisk. That's good. If we're gonna move right to explore the right neighbor, we're gonna do the same. But my right neighbor is actually has the same row, but its column is column +1. So here I'm checking if it's inside the map. Since I am adding to the column, there is a probability that I might exceed the maximum column number, which is the column size -1, because we start from 0. So I'm checking here if the row +1 is less than column size, because the maximum is row column size -1, because we started from 0. And it's not visited before, visit this node. Get its ID, push it, mark its parent, mark it as visited. Increase the step counter and show it as asterisk to know that we visited. To move left, the left cell is actually column -1. But same row. Again, get its ID if it's not visited before and inside the map. Push it to the priority queue. Set its parent at the current frontier and mark it as visited. Increase the step counter and show it as asterisk. And finally, the same for down, but the node below me has the same column, but the row is incremented by 1. So the new row coordinate must be inside the map. And that's to check that. The maximum row size is, the maximum row coordinate is row size -1. Because we start from 0 again. And same steps. After that point, we explored all the 4 neighbors of the current frontier. So we mark this frontier as explored. This was a frontier that we completely explored its surrounding cells. And we show the map. So it should show you something like E and 4 asterisks around at most. And then we go and get another frontier. Okay? Any question? We just finished it. Any question?
Yeah, I have a question. What does that pair int top do again? Is that an array or what is that?
It's a data structure, something like an array, but it's called the pair.
Oh, okay.
Okay, something like an array. Okay, but it's called pair.
Okay,
and
thank you.
to read its first value, if it's an array, we're gonna read, top of 0, for example, or second value top of 1. But no, this guy is not as similar to the array. So we do it in that way. So this is the first, not of 0, and this not second, not of 1. Not just so. If this is an array, this will be top of 0, brackets 0, and this will be top then brackets 1. But for pair, we don't do that in that way. So we do it in that way: dot first and dot second. First element in the pair, second element in the pair.
Okay, that makes sense.
Okay, what else we have? Yeah. Okay, if I exit, so there are 2 conditions here to exit this while loop. First, no other frontiers in the queue, in the priority queue to explore, and that means that you couldn't reach the goal. And in that case, we return -1 here, which means, you know, no route to the goal. The other case is that you explore or you pick a frontier, which is the goal node, and exit from that point. That point here. Okay? And in that case, there is a route. So we just make return the coast from the start of the goal node. So this function will return two numbers, -1 or whatever else. If it returns -1, that means there is no route from the start to the goal. If it returns anything else, any integer rather than -1, then there is a route, and this is actually the cost to reach the goal through that route. Okay. So let's see now the main function. So in the main function, I defined two variables. One is called start node ID, and the other is called goal node ID. The input map. Then I copy the grid into this input map, so I can play with it freely, okay, without, you know, worrying about changing something in the input map itself. Then I define the dictionary into which I will put or restore or record the parent of each node. Then I will initialize this parent dictionary with -1s. That means all parents in the beginning are -1s, or all cells have no parents in the beginning. Okay. This part is very similar to how to choose, you know, the coding, how to choose either the algorithm, Dijkstra's or breadth first search. So I coded it in that way. So I defined here a macro, this guy, yeah, called Dijkstra's algorithm. If this is defined, what's the meaning by defined? We define meaning there is a macro with that name. That what means, what I mean by defined. Then the code will do that, will do the exploration and shortest path using Dijkstra's algorithm. If it's not defined, if there is no macro called Dijkstra's algorithm, for example, if this is commented like this, there will be no macro called Dijkstra algorithm. So the exploration, shortest path, all that stuff will be done using breadth first search. So let's see. So let's keep it and go down and see if it's defined, what will happen. So I am saying here, if not defined, do that. Else, which means defined, do that. So let's look here. If it's not defined, do that. What is that? It's actually, where is it? Yes, it's actually calling the breadth first search algorithm function. The one just before the Dijkstra's function. Okay. And do some other coding here, which is exactly, you will find exactly the same in your in the coding that you have of breadth first search. Else, which means that Dijkstra algorithm macro is defined. There is a macro called Dijkstra algorithm and it's defined. Then solve using Dijkstra. So what we have in here? Something very similar to what we have in before. Okay. So I will call Dijkstra's function. I will check if the return value is something different from -1, then there is a route from the start to the goal. Otherwise, else I will see out that there is no route between start and the goal. Okay. So basically, I will start from the goal node and mark its parent. And I will trace the parent cell by cell until I reach the start goal. Once I reach the start goal, I will just exit this while loop. Okay. Here, I will draw the map again, but showing the shortest path. So basically, if, for example, this is the goal node, this is its parent. The node just beside it on its right. So to move from here to the goal, I should go in that way. So I will replace this cell with an arrow like this, which is smaller than. If the parent of the goal is above cell, it's above cell. Then to go to the goal from this above cell, I will replace this with V, which like an arrow going down. If the goal is the left cell, something in here. So to reach this node from this cell, I will put this greater than. If the parent of the goal is the below cell, I will put the sign for the exponent to mark going up. And so on and so forth with any parent throughout the shortest path until I reach the start node. Okay, so let's see example by example the number of steps and the cost through that shortest path. And shortest path here means the path with the minimum cost, not the shortest number of hops or the smallest number of hops. No, that's the stupid thing that Bridge First Stage is doing, is to search for shortest path, which means minimum number of hops path, which may not have the minimum cost. Okay, so let's do that example by example. We have 8 examples. So this is now example 1. So let's run. Oh, yes. Without any debugging or stuff. Good. So total cost is 5. Number of steps is 9. And this is the shortest path. The node across the shortest path. And here is the shortest path, step by step. And look at this node here. The shortest path is avoiding this node. And this node, by the way, has a cost of 1,000. Look. So the Dijkstra was successful in here. Now let's have another example. We have a problem. Oh, I'm sorry. Changes this one. Good. So the shortest path cost is 1,016. And the number of exponential steps is 78. Where is the shortest path? Shortest path is that way. Then you go left until you reach the goal. Let's do the same with Brett's first search. So in here, we go to 1000 and, oh, I'm sorry. I write every, yeah, 1078. So let's do the same with Brett's first. It will be 2000 as I mentioned here, but let's do that together. So to use Brett's first search, we should comment that macro definition. Okay, 79 steps, and the cost is 2000, doubles. And it actually goes in a very bad path that has, you know, higher cost. So let's check that on the map itself. Yes, look, these two cells beside the start node has 1000. Also those guys, So Brett's first search takes that route. That way, yeah, sorry, that until maybe here. Yes, till here. Then it goes down, then take, you know, right again or whatever, then goes down again. But Dijkstra is much smarter. So Dijkstra takes this route. Yes, there is a cost, but this is inevitable. There is a cell with 1000, but at least the other guy take two cells with each one with 1000. So at least you will remove 1000. Remove a cell with 1000 cost from your path. If we make example 3, this is Brett's first search again, 94 and 1000. 94 steps and 1000. Now let's do it with Dijkstra. $90, not 94, less, and 21. Okay, only 21. If we look at the, yeah. So look, let's compare what we have in here with the cost map. So Dijkstra's moves that way. This is, I'm sorry, this is Brett's first search or Dijkstra. This is, yeah, this is Dijkstra. Oh, yeah, I understand. Okay. So maybe there is something wrong here with Dijkstra, something that I just noticed right now in that map specific. Because it should go in that way, then go right, then go above, go up, then that way, then go down. So guys, let me check that again because maybe there is something wrong with Dijkstra, but let's check again. So. Oh, I'm sorry. This is not. This was Brett's first search. I'm very sorry. This was the previous output. Okay. Yeah. Now this is Dijkstra. I'm sorry. This was the previous output of Brett's first search. So yes, that's right. So look at, so the cost is 21 only, and the steps is 90. And here is how Dijkstra will avoid the, you know, these 1000 cells. So it goes down, okay, then goes in that way, and we want also to avoid those. Then it goes up a little bit, so it goes this way, then up until this one, then goes to right like this, then goes down until it reaches the goal. Okay, but breadth first search is just dump. So if we go back to the breadth first search stuff, if we comment this one, so yeah, it just, you know, so it goes through this cell here, so it consumes 1000. Okay, and just accidentally, just by chance, it's not something, you know, implemented, it avoids also those. But it's because it, you know, go right, go left, go up, go down. That's it. Not because it considers the cost when it searches. But at least there is a very big difference. Just one cell. Okay. So you have any question, guys?
Oh, Professor,
Yes.
the homework is DFS, right? Not Digestus.
Yeah, that's right. Yeah, I changed my mind. I'm very sorry. So I said to myself, okay, so based on let's first search, they do the DFS. Then I explain today Dijkstra, and you do A star. That's more, you know,
Right.
more convenient for you.
Okay.
Okay. Next time we'll go into something completely different. You know, we will not explore cells anymore. It will be let's say something, you know, very different. Okay.
All right. Sounds good.
Okay, guys. Any other question?
Mr. Mustafa,
Yes.
could you go to the part where you were checking like the neighbors when it was going up, down, left, right?
It is that one here.
Could you explain to me again the lines 520 and 521?
520.
You
This one.
yeah, those two lines.
Okay. So basically, okay, we will explore now the cell on the right. Okay, on my right, which is a cell that has a column, the same column coordinate as me, but +1, but same row. If it's inside the map and if it's not visited before, then we can add it as a future frontier to the queue. Okay. We can explore it, we can say. So first I determine or calculate its ID. The ID is its row plus its column multiplied by the row size. Its column, its row is exactly my row, but its column is my column +1, or the frontier column +1. Okay. Then here I am pushing or putting it or store it in the priority queue that we have. Okay. So any element in that priority queue is a pair of values. Like your shoe, for example, 2 pairs, left and right. Here we also have a pair in any entry. The first element in that pair is the cost of that node, that new node. The cost from the start. So if the start wanna visit this node, it will, you know, go through some cells. In each cell there is a cost. So the combined cost from the start to that node will be stored in that first element in that pair. So what is this cost? It's actually the parent cost plus the cost of that cell. So each cell has a cost. Any cell, if you want to go to any cell, okay, if you want to go to some cell from a neighbor cell, okay, this cell has a cost, so this will be added to the cost that you already have from the start node. Okay, so this is the cost of the neighbor from the start. plus the cost of that new cell that you discovered. This will give you this addition of this summation here will give you the cost to reach the cell, this cell from the start node. And the second entry of that pair is the ID of that node, which you just calculated in that line here. Okay. Then after that, you assign a parent for that new explored node. The parent of any node is the node that discovered, or the frontier that discovered this node. And we know the ID of that frontier, which is FID. Okay? Or the frontier ID. Then we mark it as visited. We mark this node as visited so that if some other future frontier discovered this node, it will not add it again to the queue. We add any node just one time to the queue. Okay?
Okay, thank you.
Any other question?
Do you think you can move down in your code? I think there was somewhere like towards the end where I didn't understand a line of code. Oh, why do you use a percentage sign? The parent node percentage row size?
Yeah. This is called the modulus. So let's go back to the, okay, let me go back to the tablet. You see the tablet, right?
Yeah.
Good. So let's apply these equations with a particular, with any example, with a real example from this. So if you know the ID of any cell, so for example, cell 9, this one. Yes, it has a row of 1 and a column of 2. But we don't know that. We know the ID right now. And we want to, from this ID, get these two values. So let's apply. I am saying here that the row is equal to the ID of the node, mode or modulus, row size. Good. The ID is 9. And the row size, how many rows we have here? We have 4 rows. 1, 2, 3, 4. So what does that mean? 9 modulus 4 is equal to, or let's do it, 9 divided by 4. It's equal to, there are 2 4s in the 9. 4 plus 4 is 8, and 8 is still less than 9, right? And there will be a remainder of 1 over 4. And we can convert from this to this again. So just multiply this by this and add this guy. 4 multiplied by 2 is 8. 8 plus 1 is 9. So this will be equal 9 over 4 again. Okay? This is the modulus. This is called modulus. Okay? Like for example, 3 over 2. How many 2's in the 3? There are just 1, 2. 1, 2, yeah. 1. And the remainder is 1 over 2. And 2 multiplied by 1 plus 1 is 3 over 2. Okay? So this modulus here is saying how many 4's in the 9. We have 2 4's, right? Row size -1 maybe. Oh, I'm sorry. I'm sorry. The opposite. So not this one. I have a mistake here. I'm very sorry. Okay. So until this point, we are okay. Okay. Where is the modulus? The modulus is not the 2. It's that one. So this is the modulus. I'm very sorry. The remainder, we can say. So this value here is saying what is the remainder of dividing 9 by 4. How to get this remainder? Just to do that in that way here. Calculate how many 4 in the 9. There are 2, and there will be one remainder, right? 4 plus 4 plus 1 equal to 9. So this one is the remainder. So 9 modulus 4 is 1. Then the column is equal to the ID minus row divided by row size. But the integer of that division. So let's do that. Yes, let's continue here. So the ID is 9 minus the row coordinate, which we just got, which is 1, over the row size, which is 4. So 8 divided by 4 is 2. And look here, row is equal 9 modulus 4, the remainder is 1, the row is 1. The column is equal to that thing. That thing here give us 2. This is actually 0. Let's have another example. Maybe you are confused or something. Let's have another example. Let's take 14, for example. Row of that, of course, we know that this is row 2 and the column 3. Row equal to 14 modulus 4, the row size. So we have 14 has 3 fours, and there will be a remainder of 2. So that guy will give us 2. Good. Now column equal to the ID, which is 14, minus row 2, divided by row size, which is 4. So 12, 4, 3. You got it?
Yeah, I see it now. Thank you.
Good. Any other question? Any other question, guys?
Nope.
Okay. So see you next next Monday is our big day now, the drive-through event. Still 2 of you didn't send me the card description. Okay. I hope they can send it soon. Follow the instructions that I sent you earlier regarding this drive-through, okay, event, and come at your particular time slot. So to avoid any, any big interaction between people, to avoid any, contagion or something. And yeah, see you on Monday. See you on Monday. Have a good day, guys. Bye-bye.